For the last little bit today, what we're going to talk about is intersection control. So we're going to talk about what do the different control types look like, how do they operate, what kind of behaviors are associated with them, so on and so forth. So getting into it, the first thing we're going to do is we're going to look at do we have the correct control types for each intersection, and are they properly coded into the network? This also has a section that says verify vehicles are reacting appropriately to controls. This will be one of the first times that we're going to be looking at an animation. And again, I didn't upload the animation because it's a 10 gigabyte file. But sometimes you'll be given an animation. Sometimes you might need to record your own animation. But there's a playback tool where we can also look at the playback. So I'm going to demo that for you in an upcoming section. But we're going to start by looking at the traffic controls, making sure that they have the correct control type and that they are properly coded into the network. And then we want to look at and make sure that the vehicles are actually reacting appropriately. So the different control types that we have in Vissim are signal controlled, stop controlled, and yield controlled. Um, um, we technically have, uncontrolled or uninterrupted flow, but we don't really consider those as intersection control. They're just merge and weaves kind of things. So signal controllers, I've put in the recommendations from the MoDOT Vissim protocols here. So, using ring barrier controllers, where pedestrians have a measurable impact, you should be having pedestrian crosswalks or mid-block crossings. Stop control, you're looking for two-way stops, all-way stops, again, looking for pedestrian crossings, things like that. As far as where the stop signs or signal heads are physically placed, a lot of times you can just look at the aerial imagery and there will be a stop bar. But if there's not a stop bar there, you might have field data that indicates, where vehicles are stopping, or maybe that's something that your modelers will do. In addition to getting field counts, is indicating, where in relation to the stop bar are vehicles actually stopping. Because what you want to do is you want to accurately recreate what the vehicles are doing in the field more so than what they necessarily should be doing. Because if for example, vehicles are rolling through a stop sign on a two-way stop, right? The capacity is going to be artificially inflated in the actual network, right? So whereas the stop control right turn might, HCM might say it should have a capacity of 1,200 vehicles. Maybe in real life, what's happening is everyone's rolling through that stop and you're getting closer to 1,500. Which means downstream, the next intersection you see downstream is actually getting fed 1,500 vehicles per hour as opposed to 1,200. And so if that's not modeled accurately in Vissim, then you could be artificially metering traffic upstream, which could affect downstream intersection analysis. So you want to kind of play that game of how accurate do we want to be to the real world versus what should be happening per the rules of the road, quote unquote. Stop signs in particular, though, do not have any sort of yield behavior inherently associated with them. So you might go out to the field and you might look at a car that stops at the stop sign and you say, okay, the average car stops for like 2 to 3 seconds. But they're not stopping because of the stop sign for 2 to 3 seconds. They're stopping and then waiting for a gap. And so in Vissim, we model that using conflict areas or priority rules. And conflict or priority rules are objects in the network that control the gap acceptance. And so for stop controlled intersections, for yield controlled intersections, or for permissive movements on signal controllers, like a permissive left, where they're yielding to oncoming traffic, or a right turn on red, those should all be using conflict areas or priority rules to measure the gap acceptance. And then the wait times or the average dwell times on those permissive movements can be calibrated by increasing or decreasing those gap acceptances. Okay. So looking at intersection control, we're going to start with signalized intersections. That's usually the first place people gravitate to, is towards signalized intersections. So in Vissim, we have a list of all of the signal controllers in the list. Now, a good Vissim modeler will be very accurate with how they name the controllers, right? Sometimes you'll get a modeler that doesn't have any names, and so you just kind of have to figure out where signal controller 1 falls in the network. But in this case, each signal controller is named well enough that you kind of have a good grasp on where it lies in the field. So each controller, in this case, we're using the ring barrier controller, has a controller interface, and you can go into that interface and look at the timing plans and things like that. In terms of validating these, there's not a lot to it. It just takes a long time because you're pulling up signal timing sheets and you're comparing the data in the signal timing sheet to the data in the ring barrier controller. So does it have the right phases? Does it have the right overlap phases? Does it have the right timing within each phase? Is your sequencing correct? Do you have the correct red and yellow timings? Is your offset and cycle length correct? Things like that. The ring barrier controller is based off of an actual controller that is pretty widely used in the field, uh, based on 2070 logic, ring barrier controller logic. So all the fields in the Rbc editor should be fairly consistent with what you might see on your average signal timing diagram. It's just a matter of figuring out which page you operate on. Typically where I will start is I'll start in my signal timing plan, right? You'll have like 4 or 5 pages. One of them will be your schedule. And so you'll look at, maybe you're in the AM model or the PM model, right? And so you'll look at the schedule and you see what pattern should we be operating on, and are my splits okay? So you can look at your splits down below and make sure that your splits match up. And then you'll go back to that first page that says green timing and red timing and things like that, or in yellow timing, and you'll go back and you'll make sure all your clearances are correct and all of your phasing numbers are correct and things like that. There are other types of controllers in the network that you might look at, such as ramp meters. We have some inbuilt ramp meters that have a single phase. So you'll see the controller type is called a ramp meter. It has a single phase ramp meter, so it just cycles based on the flow rate, the desired flow rate that you want on that ramp meter. If you have 2-stage ramp meters or alternating ramp meters, those will be done with the type of controller will be a different type of controller called a VAP, or Vehicle Actuated Programming controller. So there might be different types of controllers that you might have to look at to validate the timing. But you can also validate any controller's timing by looking at the signal timing plan and running the simulation as well. Once you've looked at the signal timing portions, you'll then go in and look at conflict area and priority rule settings, because again, this isn't just dealing with yield-based intersections. Signalized intersections all the time have permissive yield-based movements, right? You have your permissive left turns, you have your right turn on reds, and so you'll need to validate those using conflict area timings or your minimum gaps. So for the conflict areas, you're looking at the front gap, rear gap, and then there's a safety distance factor. And then for the priority rule, you're looking at the minimum gap time and the clearance value, which is the space of the conflict. So let's go ahead and start by taking a look at the signalized intersections and then some of the permissive movements within those signalized intersections, and then we'll move on to some other types of intersections. Oop, one too far. So here what we'll do is we left off and our DTA configuration. So the first thing we're going to do is we're going to check through our intersection control. Okay. So by using our drop-down menu, we're going to select the check intersection control option. Where are we? I went too far. Check intersection control. So step 20. Here, we're going to look at our different control parameters. So I'm going to quickly just zoom in. You'll see what we call node objects. Nodes in Vissim are what evaluate intersections. They denote in Vissim, this is an intersection. Everything contained within this box is an intersection. And so these nodes are a quick indicator to identify where the intersections are. So if I zoom in on a particular node, what we can do is we can double check and see, okay, what type of intersection is this? And does it have all the necessary components? Now, real quick, at the top of the network editor, because we can kind of see through the road a little bit, but you might also like to switch to a wireframe mode, which just gives us a centerline view, which makes it a little bit easier to see the background objects. Or if you don't want to see the links at all, you can pick something else. So like instead of having links highlighted, you select signal heads. And then you can turn off the links by toggling this link button right here. And so now all you're seeing are detectors, signal heads, stop signs, conflict areas, but without the links. And underneath, you can see the aerial imagery underneath. So some things to look at here are the first thing we want to check again is we are currently on step 20. We're just checking the intersection control values, right? So what we're looking for is, okay, is this a signalized intersection? From the aerial, I can see that there are some signals here. So I'd expect to see signal heads, and we do see these red lines indicating signal heads at this location. Sorry about that. I'm going to close out my Outlook real quick. So at this location, we do see signal heads. Now, clear distinction in Vissim between real world is that the signal head object is not actually the signal head on the mast. It's indicating the stop bar location. So in this case, your red lines should be fairly close to wherever your stop bar is at the intersection. So you can see here, these are set back a little bit, but if I turn the links on, it looks like our arterial was shifted to the left a bit. So it makes sense that if our arterial is shifted to the left, for example, our center line should be right here, but our center line is shifted to the left about 14 feet. So it makes sense that our stop bars are shifted back, roughly 14-ish feet, right? And so that's just a knock-on effect from our previous look at the link alignment. Since our link alignment is off, our signal heads are going to be a little bit off. But as long as proportionally they're kind of related to each other, right? So that shift is kind of the same for both of them, it should be okay. So we see our signal heads, we see stop bar detectors. So we have some stop bar detectors, we have some advanced detectors upstream a little bit. Now detectors in Vissim are modeling a detection zone, not necessarily induction loop detectors, right? So if we look at the aerial underneath, we can't really see induction loop detectors in the pavement where these detectors are, but maybe there's like video detectors or something like that on the signal head itself. And this is the zone that they are calibrated to detect a vehicle. And so the detectors themselves should be recreating that detection zone. And so that's what you'll be looking for there. Now you can also see that we have conflict areas. And these conflict areas, again, they aren't every single conflict. Here's all the potential conflicts within the network, right? So if I click on conflict areas, it'll highlight any point that a link overlaps, there's a potential conflict. But since this is a signalized intersection, this particular conflict is protected by the signal. So cars don't need to yield to each other because this through movement and this through movement theoretically shouldn't have green at the same time. So in this case, this conflict area has been left as yellow, or in other words, the vehicles are going to ignore that potential conflict because they're trusting the signal implicitly and they're just driving through. But if we look, this northbound left, it has a conflict area, right? So this northbound left is yielding to oncoming traffic. And I can tell that because it's green on the through movement and it's red on the left turning movement. So that tells me that the left turn has a permissive left turn movement. Similarly, on these right turns, right turn on red, they are yielding to the through movement vehicles. So we have some of these yielding based movements at this intersection. So for signalized intersections, again, you're looking for your signal heads, you're looking for your detectors, you're looking for conflict areas on the permissive movements. Here's another signalized intersection, another signalized intersection. So what you're going to do is you're just going to quickly spot check and make sure that they have all the elements that they need. What I want to do is I want to find some other intersection types throughout the network. That looks like a signal, more signals. I'm trying to find a two-way stop controlled intersection. That's a merge. Ooh, here we go. Here's a two-way stop controlled intersection. So we have this little frontage road or a driveway or something like that. Maybe this was a big enough demand generator that they chose to include it. And here we have a stop or a yield controlled intersection because I don't see any sort of stop signs or signal heads. And so vehicles that are turning left out need to yield to the main line, and vehicles that are turning right out need to yield to the main line. We also see vehicles that are turning in yielding to oncoming traffic. So again, for yield-based intersections, you're going to be wanting to make sure that you have all of the conflict areas appropriately coded there. Let's go take a look because I know we have a roundabout, I think down here somewhere. Let's go take a look at that roundabout. Where did that roundabout go? There it is. Okay. So here we have a roundabout in the network. I'm going to turn off these background images. So roundabouts are coded pretty much like a yield controlled intersection in the sense that there's not going to be any stop signs. There's not going to be any signal heads or anything like that. What you're going to be doing is the model is going to have links going through, and then vehicles that are entering the roundabout will need to yield to particular oncoming traffic or circulating traffic. So here for the southbound right, it looks like we have a bypass lane, so they don't have to yield because there's no conflict. One thing I am noticing on this particular roundabout that we're looking at is, and this might come up later as well in other sections, is if we look at this right lane here, we have a dual through on this side, and the right lane or the left side lane is yielding to circulating traffic. But what happens if a vehicle is making this movement? Right? There's no one yielding to that vehicle. So this is where the roundabout operation, the way this is coded is a little bit ambiguous. What it is insinuating is that circulating vehicles have the right of way, and then they need to yield to vehicles in order to make a lane change to make the exit. Now, more commonly, what's going to happen is this is just going to shoot across like this, and the entering vehicles going westbound will have to yield to both in both lanes. So this could be a potential area where maybe there was a mistake being made there, right? So you might have instead have a link that just shoots all the way through. So they're not having, because you don't want vehicles making lane changes within the roundabout, right? So this might be something like you have a striped gore point and then you have a link just jutting through and they have to cross both and they'd have to yield to both. Um, so that's something where you want to look out for here, where we're looking at the movement of the vehicles. So kind of taking your mind away from just the lane configurations for a second. What I like to do is I like to take my measuring stick and I'll click on this circulating lane, and then I'll click on this exit lane, and that can give me an idea of what needs to happen. And so you can see that they have to make a lane change. And that's where you as a reviewer will say, is this the behavior that we want to simulate vehicles doing, right? Is this the expected behavior that we're seeing vehicles in the field doing? Or maybe if this is a future proposed roundabout, is this what we're expecting them to do in the future, right? So if we look, for example, on this movement, on this movement, the circulating vehicles can just shoot straight out. They don't need to make a lane change or anything like that. And so these entering vehicles that are crossing need to yield to both through lanes. And if they are turning right, they need to just yield to the right lane. So that's something that you might want to consider there. Also, with multi-lane roundabouts, it's very common to block lane changes. And since we have a dashed white line, that is allowing lane changes through the roundabout, typically for safety purposes and to reduce as much confusion as possible. Designers of roundabouts will prevent lane changes while within the roundabout. And so in this case, you might see a solid white line going through this section. See, I think we have another roundabout somewhere else that we can go look at, and we can double check, see how the other one was made up real quick. I don't remember where it was off the top of my head, though. I also know that this model has a diverging diamond interchange. So why don't we go take a look at that diverging diamond? I believe it's right here. Yeah, right here. So here we have a diverging diamond interchange. And you'll notice that in the way this one is modeled, both sides of the diverging diamond are modeled with two different intersections. That's very common to do at like the intersection capacity analysis level, right? Your HCM level or your travel demand modeling level. It's very common to have those modeled as separate intersections just because the way you're going to handle it. But in Vissim, these could be modeled as one intersection. It just depends on how you want to analyze the network. If we look real quick at this intersection, I'm going to double click on a signal head. It is assigned signal controller number 2. It just happens to also be phase 5. If I look at this one, it is also assigned signal controller number 2. So this is very interesting because if we look at the way the signal timing is set up, if we go into our signal controllers, signal controller, there is a single signal controller number 2 that is controlling both the north end and the south end of this. So it's controlled as if it's one unified controller, but since we have two separate nodes, it's being analyzed as two independent intersections. So that's an interesting thing that we'll have to remember going forward. But as far as the intersection setup, it has its standard signal heads, it has its detectors, and then anywhere where there's a yield point, there are conflict areas. Again, this looks like it should have a conflict area, but this movement should be protected by this signal, similar to this crossing movement. So Vissim indicates that there are potential conflicts there, but since it's protected by the signal, you don't have to worry about coding in conflict areas because it'll just, it doesn't matter anyway. Now here's a good indication of we have a protected movement, but we still have a conflict area because there could be right turn on red. And I want to show you what right turn on red looks like. So here we have a signal head for our vehicles, but instead of using the signal head, technically the vehicles are paying attention to this stop sign. So this orange bar is a stop sign. And you can see that in the stop sign editor, there is a right turn on red tab. And this stop sign is associated with a specific phase of a specific signal controller. And so what this is saying is while phase 2 is green, people can ignore this stop sign. Otherwise, if phase 2 is not green, then they have to stop, come to a complete stop, and then yield to opposing traffic. So this allows you to do a right turn on red while also having a protected right turn movement. All right. I'm trying to see if there's any other intersection types that I missed. I don't think so. These are all signal controllers. We covered the roundabout. Oh, there is a single point urban interchange right here. Oh, and there's the other roundabout. So if we look here, here's just a single lane roundabout all the way around. So we have all the conflict areas. That one looks coded correctly. Here's our single point urban interchange. Again, it's underneath the freeway. And so we have our signal heads and all of our detectors appropriately modeled. In this case, all movements are protected, so there's no conflict areas. Okay, so once you've gone around and you've validated all of the intersections have been coded correctly, the next step we want to do is look at our signal timing plans. So here, what we've done is this layout for our number, 21? Check signal timing plans. What we've done is we have activated labels on the signal heads themselves. So we can see here the labels have been activated for the signal heads, and what they are displaying are two key bits of information. The first number that you're going to see if I zoom in on a particular signal head, let me zoom in a little bit on the single point urban interchange. You see a number and then a dash and then another number. That first number that you're seeing is the signal controller ID number. And then the second number you're seeing is the phase number associated with that movement. So in this case, this signal head is signal controller number 7, phase 1, signal controller number 7, phase 6, so on and so forth. So to check the timing, what you'll do is you'll come to this intersection, you'll double check that all signal heads are in the appropriate location. And then for the specific timing, what you'll have to do is come into your signal controllers menu. And find in your list of signal controllers, you'll want to find signal controller number 7. So here we have signal controller number 7. If we click on it, it's our single point urban interchange. And on the right side, you can see all of the phases that are associated with this controller. In this case, we have phases 1, 2, 3, 5, 6, and 7. Unfortunately, though, we can't really see any of the green timing or any of that. So what we'll have to do is double click on it. So double click on where it says controller number 7. Here you can see what type of controller it is, and you can see we have a lot of different types of controllers in the network. And then in this menu, you want to click this Edit Signal Groups button. Before I do that, though, I'm going to take my controller. I'm going to put it off to this. I'm going to put my intersection off to the side so we can better see it. So we've double clicked on signal controller number 7, and now we're going to click this Edit Signal Groups. In Vissim, a signal group is just a generic term for the RBC. When you're using the RBC, it's synonymous with a phase in this case. So Edit Signal Groups. This should open up the Rbc Editor. Up above in the notes, you can see it was created via the Rbc API synchro importer. So it looks like they imported the signal timing. And what we can do is we can go up to the view and we can go to basic view. And what the basic view will do is it will show us some basic settings, right? So it'll show us our phase numbers, the maximum green time, the yellow time, the red time, any recalls it might have, the sequence, and then down below, you might have to expand this up arrow. You can see the sequencing down below. And then on the right here, you'll also be able to see the pattern. So in this case, the cycle length and the offset. So in this case, we're using pattern 1. The cycle length is 100 seconds. And we can see we have phases 1, 2, 3, and then 5, 6, and 7 in our signal planning diagram. Now in this Rbc editor, all of the timing is going to be in this box right here. This kind of mirrors your Vissim. See how we have the network editor, we have objects list, and then we have some more information down at the bottom. The Rbc interface kind of mirrors that pretty well. So we have our object list on the left, where you can find different types of signal control settings. We have our quote unquote network editor, where we can actually edit those timings. And then down below, we have some more information about the phasing in the diagram. So on the left here, you can activate, if you want to see, for example, minimum green, you activate the minimum green value and you can see what the minimum green value settings are. If they have a walk phase or a flash don't walk phase, you can see what they look like. Or if they have a minimum recall, in this case, phases 2 and 6 have a minimum recall. In the patterns section, we can look at pattern 1. And so I can turn on pattern 1. And we can see the split settings and then any custom settings that they have specifically for pattern 1. So in this case, phases 2 and 6 are coordinated phases. So you can go through and you can look at different settings. I'm going to turn off pattern 1 real quick, and I'm going to turn on detectors. So we have detectors 1, 2, 3, 5, 6, and 7, and they're controlling signal phases 1, 2, 3, 5, 6, and 7. You might have other detectors, like instead of just stop bar detectors, you might have pedestrian detectors, or you might have queue detectors on your off ramps or on your on ramps. And so basically what you're going to have to do when reviewing signal control is it's kind of a tedious process because there's not just a quick overlay that you can do. You're just going to have to pull up your signal timing plan and just validate that everything makes sense. For the most part, you can look at this diagram down below. It'll give you plenty of information about the splits and the sequencing, and then you'll just look for the cycle length and maybe some other specific things. Now, if you're doing anything, for most intersections, it's going to be fairly straightforward. The Rbc does have preemption and transit signal priority. So if you're doing any sort of bus rapid transit, or maybe you have a heavy rail or a light rail line that's crossing an intersection, it might have preemption or transit signal priority, in which case you'll have to go validate those settings as well. So you can just turn on that section for preemption, for example, and just see if any preemption is active, right? Even if you don't have heavy rail or light rail, you might have emergency vehicle preemption or queues. If a queue backs up on a ramp too far, you might have a queue detector that triggers a preemption to flush the queue. So in that case, you'll want to validate and make sure that the preemption has been coded correctly there. Once you're fairly confident with that, you can always click OK and close out of it. One other thing before you do that, though, I want to show you, and this is an underutilized feature, but being the reviewers that you might be, where you might be coming across very similar sets of timing plans and things like that, what you can do is after you go through your first signal controller review, as you're reviewing it, what I would recommend you do is be very diligent about activating and deactivating the rows and columns that are actually being used in that signal timing plan so that they're all visible and only the parameters that you're using are visible. So for example, pattern 1, you probably don't need all these extra ones. So you can come in here and you can only turn on, for example, splits and coordination, right? So you'll find the coordinated phases, right? You might only need those ones. For vehicle detectors, you might come down. You don't need pedestrian and queue detectors. Maybe for vehicle detectors, all you need is the detector number and the calling signal group, right? And so you can customize your view, and you can go up to view and you can say save settings. And you can say, for example, I might do Levi's review settings or something like that. When I save that and close out, just a second, it's taking a second to save. Click OK. Now I can go to my next intersection, open it up, edit signal groups. My Rbc editor should open here pretty quick. I go to view, I can say load settings. I find the review settings that I previously saved, hit open, and it will pull open all of the different parameters that I previously selected. So if you're doing a lot of signal controller review, this could really speed up the process, right? Because you're probably going to have the same 10 or 15 parameters that you're going to look at in 90% of your intersections. And so having a predefined layout file, a settings file, will really help speed up that process. So you're not spending time clicking on the individual parameters every single time. And if you ever need help in the future setting this up, like maybe you get to your first review and you have your signal timing plan and you need some help setting it up, I'd be more than happy to follow up with you. Just shoot me an email, and I can do that for you as well, or with you as well. All right, so you're going to go through, you're going to review your signal timing. The next one we have is a drop-down menu for ramp meters as well. So you're going to want to look for any sort of ramp metering and timing. In this case, I don't think these ramps have any ramp meters. I didn't see any in the controller list. They all are RBC. But just real quick as examples, I'm going to open up a training directory. These are preset examples that are installed with your software. And so if we need an example of a ramp meter, for example, we have a built-in ramp meter using the ramp meter functionality. So I'm going to open that up so you can just kind of see what it looks like. Just give me 1 second while this opens. So here we have just a short freeway segment and then an on-ramp. So what a ramp meter we have is on the side of the network editor when you're building out your network. You can press a button that says Create Ramp Meter Facility, and it'll walk you through building out a ramp meter. And you can just do that and then hit the check mark, and it'll automatically create this ramp meter in the list for you. In this case, we have this one predefined. So if you do have one of these predefined ramp meters or out of the box ramp meters, it's going to look like this. You're just going to double click. There's no Rbc editor or anything. It's just going to have the type ramp meter. And you're going to look at the signal groups option. And you're just going to see what the settings look like here. So it'll have a minimum green, a minimum red, so on and so forth, values there. And so there's not a whole lot to them. But that's just for a 1-lane ramp meter. If you want to have multi-lane ramp meters, you can't use that built-in one. You'll have to use a VAP controller. And so a VAP controller is just another type of controller. VAP stands for Vehicle Actuated Programming. And so in this case, we have two different phases on the same ramp meter. And in this case, a VAP controller is basically like a script-based controller. And in the file directory, you'll see a VAP file here that will have the logic of the ramp meter. So here's the ramp meter logic that we have. based on a 2-lane ramp meter, right? So it's kind of tricky to go through, but unfortunately, that is the VAP ramp meter that you have. So just depending on the type of controller, if the type says RBC, you can view it in the RBC window. If it says ramp metering controller, that is just the 1-lane ramp meter, and if it's a VAP, that means it's a script-based controller, and you'll have to go look through that script logic and make sure that it kind of makes sense. Okay. So once you feel comfortable with all your signal timing, where are we? The last thing that we're going to talk about today are conflict management. So coming back to our conflict areas just real quick, on all our permissive movements, we have our right turn on reds, we have our roundabouts. What you're going to want to do is you're going to want to double click on a conflict area, and that will open up the conflict areas list. And then you can go through and spot check any conflict areas in the network and see where they might be adjusted or calibrated as such. In the conflict area list, there's a bunch of conflict areas. So here we have 885 conflicts in the network. And this is including even the yellow conflicts that aren't accounted for. So for example, if we look at conflict areas like on this single point urban interchange, this conflict it doesn't exist because it's an overpass, right? So these cars that are swinging under the underpass aren't worried about the freeway. So that one we could ignore, right? Here's another one where these southbound left turning vehicles are conflicting with the westbound through vehicles. Again, that's protected by the signal, so we don't have to worry about it. Any one that is considered yellow or that we can ignore is called a passive conflict area. And you can see that in our conflict areas list under status called passive. So what I like to do is I like to filter and I say does not contain passive. And so now instead of 885, we have only 115 conflicts that we need to validate. And most of the time what we can do is we can do it all from the list. You've already spot checked to make sure that they are appropriately assigned the yield behavior. So you want to make sure that the red is on the inbound and not on the circulating, for example, and stuff like that. But now what we want to do is we quickly want to spot check the parameters. So the parameters we want to look at are the front gap, the rear gap, and the safety distance factor. These all have to do with the gap acceptances. And the common rule that you can kind of go by is that for any driver behaviors, whether it's conflict areas, priority rules, or like driver behavior parameters, the smaller the driver behavior value is, the more aggressive people become. And so theoretically, your capacity might increase a little bit, right? So if our default is half a second, and then 1.5, this value is actually multiplied by the headway of the vehicles. So it's taking the minimum headway and multiplying it by this factor. These are all the default values. So what you're going to want to look for are any values that are not the default. So for example, we can start filtering and we can say, let's look for anything that does not equal 0.5. Okay, so none of them have an adjusted front gap. Let's look for any of them that have an adjusted rear gap. So we're going to say 0.5 and we're going to say does not equal. So none of them have a calibrated rear gap. Okay. So then the safety distance factor will do the same thing. The default is 1.5. So I'll look for anything that does not equal 1.5. And it looks like all the conflict areas were coded, but none of them were calibrated to give more or less gap acceptance. They're all just using the default values, which isn't bad as long as the output values that we're going to look at tomorrow are correct and the throughput and the capacity are correct. But for something like a roundabout, the conflict area is directly responsible for the capacity of the movement. So if we look tomorrow and the capacity of this roundabout's too high, then we could point to the conflict area and say this needs to be more conservative, which means that fewer vehicles will be able to pump through. It'll drop the capacity a bit. Some other factors we want to look at are the additional stopping distance. So by default, cars want to put their front bumper right on the edge of this conflict area. But if we look at our roundabout, in this case, this roundabout doesn't have a stop line. Sometimes you'll see like a sawtooth stop line or something like that, in which case what you'll do is you'll measure back from the conflict area and you'll figure out, okay, let's just say that the stop bar was offset by 15 feet. Well, this additional stopping distance then will need to be set to 15, and that will make it so the cars stop farther away from the conflict. And then we have anticipate route and avoid blocking. Basically, avoid blocking will mean if that the cars on the major movement, on the green movement, say there's a queue over here because there's pedestrians crossing or something, cars will not stop in the conflict area. So that's what avoid blocking does. Anticipate route, this is very useful for roundabouts. So if you are a car that is waiting to go into a roundabout and you see 2 or 3 cars coming around the corner, depending on where you are and the driver culture of the area, again, I haven't really driven in this particular area myself, so I don't know what the roundabout culture is here. But in some areas, it's more common to turn on your turn signal if you're going to exit the conflict area. And so cars become more aggressive because they see that right turn signal is turned on, and so they'll jump out in front of that car, expecting that car that would otherwise be conflicting with them to turn. That's what this anticipate route does. So if the anticipate route by default is set to 0, that means that the car that is waiting to come in will not know if the car is turning right or if they're going through, and so it will wait until the car commits to exiting before it enters. If we set this anticipate route to something like 100%, what that will do is that will make it so that it will know for a fact that that car is exiting or for a fact that that car is circulating, and so it could theoretically jump out sooner, which might increase the capacity a bit. So just depending on the driver culture, by default this is set to 0, but what I'll do is I'll just sort descending and see if there's any, I'll hit sort descending to see if any of these are set to not 0, right? And I'll sort this one by ascending and see if any of them are set to not 100. All right. So that's how you would look at conflict areas. Priority rules are another type of conflict management tool. They're kind of like a conflict area, but you can kind of put them wherever you want. So conflict areas show up specifically wherever any links overlap. Priority rules show you can customize where they go, and it's kind of like a custom created conflict area. So real quick, going back into what their settings are, because we don't have any in this model, you're going to be looking, instead of looking at the front gap, rear gap, and safety distance factor, you're going to be looking at this minimum gap time. And this is just seen as like a critical gap, right? And so this is just, what is an acceptable gap to merge into? If the gap is bigger than this value, then you'll merge in. If not, then you won't. So you can kind of think of it like a critical gap value.